Today, I will probably spend more time doing the problem in US units in addition to metric units. Last time when I did this, I just did it in metric. What we were able to do the first time I tried doing a class in IViewOps is we were able to set out simple plan up to the end of the secondary treatment system. The objective of this this course, for those who already have a license, it's a training course. For others, it's more of a webinar. The objective is fairly simple: is to get you going and running a simple plan. The objective is not to be right at this level to be able to simulate completely with all the features an actual plan. Obviously, an actual plan is far more complicated than what can be done in 1.5 hours. If you are thinking of an actual plan with all the features, this can become an involved project depending on what all you would like to do. For example, you can run a project to refine your asset knowledge, to refine how assets control your processes, the availability of your assets control processes, how to analyze your plant hydraulics, how to refine your process kinetics. So it's essentially a 3-layered architecture with assets, hydraulics, and then process kinetics. So that is the key difference between let's say, those of you who use BioWin and GPSX, which are essentially process kinetic models put into a design framework. This is geared more towards managing your plant and your utility, and managing your assets, managing how you will upgrade your assets, understanding hydraulics and how they. What I would ask you to do once you are able to join, put your computer on your side, or put your microphone on mute. I think GoToMeeting allows that. Otherwise, what I'll have to do is I think someone is not on mute. The only other way I can do it is I can try from this side. Okay, let me try. Okay, someone who joined in just now. Okay, I'm going to try and mute everybody from this end. If it is still, if you cannot hear me, let me know. Okay, so. I'm speaking right now, but I don't know if you can hear me from your end, but maybe someone can give me some feedback. I'll just put it in the chat session. Okay, so just a brief recap since some just joined. Today we will set up a simple plan starting from scratch. I'll start from a blank screen. What you see over here is essentially the plan we completed the last time, but then there were some other additions made for anticipated project at Thameswater in England through one of their local partners over there. Last time also what I did was I did it in metric units. Today I will try to do the same in English US units and then just switch you back to metric, which is pretty simple. So at this time, what I'm going to do is I'm going to start a new plant. I am going to just show you where the files are when we start IViewOps. What happens is when you're working with IViewOps, it separates the configuration that you create from the data that you generate as a result of steady state or dynamic simulation or optimization runs into separate files. So whenever you start a file, you will see a file called IVO. Those who are using a beta version or the early version, they would have seen an AWTR file. IViewOps2, which is the non-beta version, saves it as an IVO file, which is at the base an XML file. And we used XML because of portability issues and for managing multiple versions. After this, we switched away from what was a binary save before, which created issues with backward compatibility to an XML save, which is the same as how the current Excel files and also. The IVO1 file is generated automatically at the time of save, and this will contain the data. So if you see over here the basic plant 1 that we did the first time, the file size of the configuration file is much greater than IVO1. That's because we had not run the file as yet. But then when I ran it with time dynamic simulation, you can see that there's the IVO1, I renamed it client 2. The IVO1 file is much larger in size because it is holding the data for all the time steps in it. There are various other ways to manage files, including we have what we call JavaScript object notation built in, which allows us to create, if it is a project with utility, create little output segments which you can see on an Android phone or even an iPhone, because JavaScript object notation works with those. This other file that you see here, you can save the kinetics that you have created. If you have created your own special kinetics for this plant and you want to retrieve it and use it in another plant, you can save your kinetic parameters into a file that I will just show it to you when we are going through it. So that kind of gives you a background before we start fresh today. And I do not think there is anybody today, maybe Kevin is, who would be trying to also replicate this on his own computer. There were some in the previous class who were using their license and using it as a learning tool rather than just a seminar. But you could do that, and I'll start slow, and then towards the end, I will speed up a little. We will go for 1.5 hours. If you cannot stay for the 1.5 hours and you want to join tomorrow's class is an hour later. It starts an hour later, and it will focus a little bit more on some of the asset management aspects that are being built into the application. Okay, so rather than stay on this file, what I'm going to do is I'm going to okay, I probably should start all the way from the beginning. I should just close out and say, so when you have IVops installed on your computer, you will see IVops2. This is IVops beta, this is IVops2 here. So I'll click on IVops2. It is fairly simple if you want to just use it like you have used GPSX and BioWind, you can, if you're familiar with those and you just want to stay at that level, in 2 hours you can set up a plant and do it for your design or some cursory level planning analysis at that same level of detail. But again, the driver for developing IVops and why MDE asked it to be developed for optimization, to troubleshoot, optimize, figure out where the bottlenecks are, is far more in-depth. So there was a lot more effort that went in. But even before we started this, as some of those who were associated with Virginia Tech, including my professor, was there were about 15 years of work prior to this. So when you get into IVops, I just opened up IVops. You will see a top menu over here. And when you go through the user manual, the IVops user manual, which is being updated for IVops too, but I think the first 3-4 chapters are pretty much, you can follow along. There are several things over here that you need to be, you will become aware of. They may look complicated initially, but it'll become very intuitive over time. The units are important. This is where you select SI or US units. So when we start a plant, you can, or at any time you can switch in between. So that's, I think, at the most elementary level, you need to know that. The asset manager is something I will touch upon tomorrow. That is something which is not available in process models. It is more for intelligence, adding intelligence and providing intelligence back to asset management. It does not replace your Maximo or J.E. Edwards or Synergen system, which is more for work order scheduling, work order management. It does not replace a Viva or Team Plan, but it provides you real-time or daily or weekly, whichever way you want, or even for planning level, how your process and hydraulics and the limitations over there and the availability of assets are playing with your risk scores and how your risk scores may change over time. So it is something which those cannot do because they are Maximo is not a process kinetics or an asset and hydraulic connected to process kinetics model, so it cannot do that. Neither can Riva. So those are important things to know. And I speak here because I also had a very large asset management practice. It's a $400 million a year utility. So I know the limitations of this. And there is a need, not just in the wastewater space, but drinking water and all other spaces, for how your risk can change because certain assets become available or unavailable or are reaching end of life or reaching certain capacity bottlenecks because you have had growth, and how you can manage. Now, unlike other systems that you have, a plant is a network of assets, and this is where it becomes very important. You can, if you run out of capacity in your secondary treatment system, if you have more primary clarifiers, you can put those online, and as long as the optimizer can figure out a way for you to manage your permit and stay within some energy thresholds that you want, that's where this comes in. It tells you how to do those along with the optimization. To run optimization, which we will not do today, you will use what we call the operator, where you set up your thresholds that you want to optimize to so many megawatts of energy use at any hour or at a certain hour of a day or on a whole day basis. And you want also to achieve a certain effluent threshold at different, either it's on weighted average or at different times of the day. That's where the operator comes in. And it works with the optimizer and helps you figure out how to optimize and which assets to put online. You can use optimization on a yearly basis or a 6-month basis or monthly basis, or for just figuring out if you're anticipating 7 days of wet weather flow, where the flows are going to change, you can use it that way. You can use it daily, once a day, or you can use it even on a 15-minute basis and you can use the information every 2 hours. it does grab data from your SCADA system if you make it available, or from an Excel file, which is written to from SCADA, and it brings that in, it runs this, and it provides you information in what we call a dashboard. The dashboard is over here. We will cover a dashboard. The dashboard is very much like your, like equivalent to your SCADA screen, except that it is a separate thing. If you run the optimization, it will tell you what your current set point is, let's say for DO and for nitrate recycle obtained from your SCADA. What the best set points should be if you run the optimizer for today or for this week, and it will provide that feedback, and it leaves it up to you whether you want to use that or not. You can also use the dashboard and optimization for just the planning and like asset level. You can say, I'm going to have 10% more growth in my sewer network. What is my optimal way of operating? I can do the discovery using it. Now, today we will use most of this. These are very simple things. When we put an icon into the screen, you can rotate it, you can flip it, you can move it right, up and down. We will also use this part, which has the types of simulation. You can do steady state or dynamic state. But as you get more sophisticated, and if you're using it in a plant, we will use what we call scenarios, where actually we run the dynamic state in a separate scenario than the steady state, because we want to be able to do certain things. Scenario is not something that is available in the other software that you have seen, but I will try to show you a little bit of how scenario works today, but I think it's more for an advanced class. You can just solve it, or you can use the optimizer to optimize, and it will then run through several combinations that use allow the plant, like you want to change your DO in combination with nitrate recycle, you want to change your wasting, what you want to change at what frequency. Some are changed every hour, some are changed every day. It will help you find. There is the other thing called offline and online. We will operate in an offline. Online is only if you want to automatically talk back to your SCADA, bring in the data, and then run it, say, once a day, and optimize, or run it once every 15 minutes, in addition to once a day, and have different optimization routines for different things. The model is something those who use BioEng, GPSX, and all are familiar with. You have the components over there, and you can select which components that you want to run. And so those who are working with process kinetics models will be familiar with SF, SA, SUF. And I will not go through this in this class. I will just set it up, and those who already have a license will get the file back so that they can work on their own. So there are the soluble components, there are the particulate components. So what you see in the other advanced process kinetics models, all of it should be here. And the types of microorganisms, including like you can select here, ordinary heterotrophs is selected. If you want to run the fermenters, you say, okay, we want to run the fermenters. If you want to run methanogens, you say, yes, I want to run methanogens here. But if you do not want to run it and make it faster because you do not think those types of microorganisms are dominant in your system, let's say you do not even have an anaerobic digester and you don't keep much sludge in a holding tank under anaerobic conditions, then really you do not want to slow this thing down for a little bit of methanogens that may be there, especially if you are thinking of using it in your plant for optimization. Speed is important and efficiency is important. And so you don't want to, where you need a Jeep, you don't want to bring a tank in to do the work. So that's the concept here. Then you have the methanogens and the methanotrophs. So this one is using the methanol, using bacteria. You can turn that on or off depending on whether you're going to use it or not. You can keep it on if you want. One of the things we don't like turning on because it creates a confusion in the thing is you do not want to turn on the Anamox unless you are you are designing an Anamox part of the plant where you want Anamox to be a significant population. in a normal plant, typically anammox will get weeded out unless a few years in the future we figure out a way that in a normal plant you can still get your anammox. By the way, I'm already working with a plant which will probably be the first plant in the country to head towards becoming energy neutral, a full secondary treatment system plant. One of the gentlemen on this thing is also working on it. So it is not that you need to run anammox to get to the lowest energy production. In fact, the people at IViewOps are operating at a pretty energy efficient point, even without having to go this route by lowering the DO in the bases and managing the process. Then you have the particulates over here, and what you see over here, by default, the ferric and aluminum is turned off. But if you're going to use, let's say, iron, or you're going to use aluminum, turn those on and run it that way. If you have a anaerobic digester, and these, okay, there are some spelling errors here which we will correct. If you run a digester and you expect through-white, Bruchite, Vivianite to form, you turn those on. So in a real plant with anaerobic digestion, these are all turned on. Okay. So then you have the processes, and within the processes, you can see that we have, as a default, certain processes are turned off, but you could go in and turn other processes on, like you could turn the fermenters on, you could turn the methanogens on. But you can see the anammox is turned off and the precipitate formation is turned off. But if you're going to use, if you expect a precipitate to form, you can turn it on. Then going under the models, you have certain parameters. Now there are three, at this time, there are three separate models that are there that are solved, and they have their own set of equations. The SGM is the suspended growth reactor model, and you can have the SGM operating in even an equalization tank or a clarifier. You can turn a biological model on in any object or a process model. Within this, you will see ordinary heterotrophs, and within the ordinary heterotrophs, the kinetic coefficients are separated to general, aerobic, anoxic, and anaerobic. And I will not go through this in today, because then we won't, if we try to do that, we won't get to the main part of the class. But other microorganisms, the fermenters, the methanogens in your digester, the polyphosphate accumulating bacteria, the methanotrophs using methanol, the AOB, ammonia oxidizers, nitrite oxidizers, anammox. And then there are coefficients for hydrolysis, which we do customize when we are calibrating it to a plant. And there are some stoichiometric coefficients here. And then there are some conversion factors, which one of which we will change as we work through today, which is the biodegradable COD to BOD ratio in your plant. The default is 1.5, but most plants are a little higher than this. For the biodegradable part of the COD to the BOD in the inflow is probably around 1.75. So I can change it right now, right over here, and save it, and say okay. It'll save that for future use. I won't cover BGM. In the PCM, there are some kinetic coefficients and all. I think it's best to cover it in another class when you're working with a real life plant. But there is one, the Henry's law constant for CO2 coming out of it after you irradiate with the partial pressure of CO2 and all that stuff is already built. It's used in pH calculation. For a digester, obviously, you'll enter a local partial pressure of carbon dioxide. And when we do a whole plant model with an anaerobic digester, I'll show you where that is put in. And then you have the coefficients for ferric, aluminum, etc. Okay. So now that this part is covered, I will cover the options when we start the run. I will show you that. And then the run button is here. You can attach different files. You can attach Excel files. And in the asset management class, I'll show you how to attach drawings and details of where a valve is inside under a road somewhere, which may take you, like if you have a problem and you discover that there is a particular valve here which throttles or is used to divert flow, and you want to attach it to a particular asset here and have that knowledge built in, you can do all that. Okay. So now let's get started with this part. So when you mouse over here, you will get into this part, which you can dock if you want. I can temporarily dock it, and you have right now over here an asset node hierarchy that will be created. The modules for your plant, you have all of those here and we will start with influent, and then we'll use some of these, the screens, pump stations, etc. Secondary treatment and tertiary, all these modules. Now, out over here, you'll put in the attributes of each of the modules. So I'm going to undock this and just float over here when necessary and grab a module and put it into the screen. And you can adjust these, you can adjust the spacing. It is better to use a high resolution screen and the fastest computer you have. Definitely, this is running, this is a slightly older computer, but not an ancient computer. But an i3 or an i5 processor is good if you're putting it in a plant for optimization every day and you're going to run many scenarios every day. You use an i7 for that. It'll help you out. So we start with an influent. I will drop an influent. To drop it, it's very easy. You just go mouse down on it and grab it and put it. Once you start using it, it will be very intuitive. What I did is I dropped a simple influent. In a later class, I'll talk about a complex influent which automatically adjusts for how much INI you're getting. And so once you enter your baseline average dry weather influent concentrations, you're not dependent on getting a COD data every day or every minute or 15 minutes or whatever, and a TKM data which you cannot get every 15 minutes anyway. The model will automatically in a complex and adjust for the INI contribution and dilute out your influent concentration as your flow changes. It will also, if your flow decreases below your baseline for which you entered it, it will concentrate the influent. So I use that with real life plants. But for that, you do have to spend some time gathering your baseline data. So today I'll just use a simple influent, which is influent S instead of an influent You can go in here anytime you do this, and it's good practice to rename. So I'll call it raw influent. Okay, but you can call it anything you want, or typically what the plant is calling it. And this becomes a method of having a good dialogue with the plant, and you can troubleshoot a plant while not being at the plant with much better tools. So we call this a raw influent. And within that, you now have to start thinking in terms of assets. Okay? And over a period of time, you'll realize the value of that. A raw influent is separated out into a child asset called the raw influent flow control. So this is, think of it as if it's a measuring device. So I'll call it just a raw influent. Or your flow meter. Think of it that way. With the meter and then the sensor on it. So within the flow controller, when I put it in, it came in with a default flow. But today, for this class, I will use US units. Okay, I'll use US units, and I'll start with a small plant. I'll start with a small plant. What I did, when it changed the units, it had a default flow of 5,000 meter cube per day. It changed it to 1.2 MDB. I'll change it to 2.5 MDB. Okay. Now, you can select your units over here. You go in here, and there is a drop down, and you select whichever units you want for US units that default is. Now, later on, if you have some time, I will, and I think I will spend 5 minutes linking up to an Excel file and bringing in time dynamic data, which will then start making you think, okay, how you generate that file from SCADA and bring in time dynamic data from SCADA. You could do that. So for dynamic simulation, that time series data, I will set this up later. We won't do an optimization today. We won't set up monitors. The monitors are associated with the operator and the dashboard, but that just gets too much. Now, the data that you get from the lab is treated as another asset. Okay. Now, you will have to start thinking of physical assets and virtual assets. And it's not just in this world of wastewater that you have virtual assets. You can have virtual assets in other things, in drinking water plants and other systems too. A virtual asset is like your SVI reading in a clarifier. It is a property of your biomass, the SVI, and it is treated as a virtual asset which drives the efficiency of your clarifier. So if you can think along those lines of a virtual asset, then you can start thinking, okay, raw influent, what we are doing is we are treating the lab data as asset. Actually, what it does is it treats the TSS as a separate asset from the BSS, etc. And if you open it up, you can have a TSS monitor and you can have different TSS at different times of the day if you wish to, and people feed in over here. So instead of going into that complication, you can open or close a hierarchy by pressing on this thing. So I'll just go here. And then if you go into the attributes, you'll see a summary section and you'll see a main section. Now, I will spend probably 5 minutes on the raw influent because it does affect the rest of the plant. What is best is to have real raw influent data. Not some data that is fictitious, because then it may turn out to be not something which is credible. So we will set up a plant which is a newer plant with a lower level of INI, and we'll start with the default data is from up to real plant Westminster, but we will set up something with 500. Let's say the raw influent is 500. Now there are some checks and balances built into this, and we will run into when you enter the data. Let's say the TSS is 200, but again, I would urge you to think of real life data, and let's say the BSS is 180. So it automatically will generate an inert TSS based on these two numbers with usage. Now you cannot see probably on your screen that this is shaded a little bit in gray. That means that you will not be able to enter, you will not, when you try to enter values for this, you will not be able to enter. I like to use some VFA, but you can leave it at 0. And let's say, and you will have to enter some fraction of fermentable COD. It's somewhere between 50 and 80%. We start with 50%. We do not know this number, start with 50% or 80%, somewhere in that range. Proceed down. So the soluble COD. Now you may say you do not have soluble COD. Well, then estimate that from your BOD numbers using, let's say, a COD to BOD ratio. But in this case, let's say the soluble COD is 200. So automatically, it will not let you enter particular COD. It automatically computes this out as a difference between 500 and 200. Yeah. It does ask you for soluble, non-biodegradable, and particulate non-biodegradable. We'll leave these as the default numbers. Okay. Now, this BOD number that is generated here is from the model over here, and when we went in here into the SGM, and we went into the conversion factors and we gave it 1.75, it used the biodegradable part of the COD to BOD ratio to figure out the BOD. And this is pretty close to plants, at least in the mid-Atlantic region. If you have a 500 COD coming in, this UV number is pretty close to what you may be observing on your run. Now, let's get to this TKN ammonia SKM. Now here, if you try to, let's say this TKN is 21, which is obviously not correct for a 500 COD. And this ammonia is too low. So we figure out that our ammonia at this point is 30. Okay. So I try to enter 30, it will give me that it will not allow me to enter it, and you'll get stuck. So I'll put it back at 15. What it wants you to do, the way it is built in, is you enter your TKN. Let's say the TKN is 45. Okay. It will not allow you to enter an ammonia which is greater than your TKN. So then you enter your SKN, let's say this is 33, and your ammonia is the nitrate is over here. Let's say it's 0 in influence. Then you enter your non-biodegradable SKN and particulate non-biodegradable nitrogen. In your plant, if you have digesters and all, this may be a little higher number. Let's say this is 0.75. Okay. And if this does not have, if you don't have anaerobic digesters, this may be more like 0.25 to 0.5, depending on whether you take septage or not. Then you have a phosphorus series. Again, if I try to enter an OP greater than the TP, I'll run into problems. So let me first put in a TP. Let's say this is 6. Let's say the total soluble phosphorus is 4.0, and let's say the OP is 3.5. And then your non-biodegradable parts of soluble phosphorus, and let's say your alkalinity here is 250. So we got this point. There are other things that you can enter, especially if you're going to form precipitates in your digester, like magnesium, things like that. If you have these values, or you can leave it at the default value. Dissolved gases, if you have some DO in your own fluid, typically it's very little, let's say 0.1, 0.0. You can leave the microorganisms in the raw influent to be 0. If you suspect there is some microbial activity and all, you can enter a little bit of OHO in your raw influent, a little bit of OAFs. These are the fermenters in the influent. But it doesn't matter if you just leave it at 0 for this level of monitoring. Okay, so we finished with the raw influent. Now we'll start getting into a real plant. What I'll do is, let me drop a screen over here. Okay, so this is like your headwork screen. Now, if you have recycles coming back from dewatering, I would have the dewatering recycle probably come in over here, and I would put a combiner here to combine that recycle with this stream. Now, in this screen, we allow you very little flexibility, at least at this stage. You have what we call, okay, how much of your solids are getting removed, and along with that, it will also remove that fraction of the particulate matter. And here we are seeing only 0.25, and it's less than 1% of the particulate matter is going to get removed in the screen. You can change this number. There are 3 different ways of entering what is getting removed. We will discuss that when we get to CARFARs rather than here. Now, to join the flow, it's very simple. You click on this, it becomes red. You click on this, it becomes green, and you get a flow line. When you run the model later, and you go to the flow line, you will get an output data of the characteristics in the flow line. So the screen, let's rename it and call it very raw influent screen. Just so that the asset names stay on track over here. In the raw influent, I will call it here when we got to lab. So now you have raw influent screen. So then I float back here and I select, okay, I want to put in a grid chamber. Okay, so I just dropped in a grid chamber. And same thing, but in a grid chamber, they right now ask you for dimensions of the grid chamber, and you could enter, okay, let's say this is a grid channel, 6 feet deep. And I'll go through the grid chamber just to give you a feel of what all you will encounter as you start setting up any asset that has tanks in it. So this is a grid tank. And so now it is asking you, some other things down here. And you can just leave it like this with default values for the grid tank, it won't matter. But if you want to start replicating your plum and you want to turn assets on and off, that means your trains are on or off, or grid tank is on and off. You go in here and you can say, okay, I want to put in 2 grid tanks. Okay, so then I'll name this grid tank group. Okay. And within this, you can now say, okay, I have 2 rectangular or 2 circular grid removal, like a circular piston grid or a rectangular grid channel. How do you enter 2 rectangular tanks? Well, you will use the same method everywhere. And what you do is you get into, it's in the user manual, you get into the cell section, and you click on the 3 dotted lines here, and then it gives you a choice. Okay, I have a rectangular cell. Do I want to add another one? I say yes, and then it says, is that other one circular or rectangular? In your plan, if you have one rectangular, you should have another rectangular. Otherwise, there is a way to handle a circular and a rectangular, but then we just put 2. We like to put 2 process objects or modules as assets on the screen, one for the circular side, one for the rectangular, and have a splitter splitting it. Here I say another rectangular cell. Okay, so now I have 2 rectangular grids. So I can rename this to be grid tank 1. And we say, okay, this length is, let's say, 20 feet. And the width is 3 feet. Just highlight this, erase this, and put your new dimensions. And the other one is grid tank 2. And this one is also 20 feet by 3 feet. Okay, now there is something which is important, which will start simulating reality in your plant. You can turn a tank on and off right through this GUI, or you can have it connected to your SCADA through this on-off controller and a link to a file generated from SCADA, which turns tanks on and off, which turns pumps on and off, blowers on and off. So the value of this and the objective of this is to, as closely as possible or as closely as you desire, to simulate reality rather than a theoretical design condition which may not, even if you're using all your plant today, a theoretical design number for a pump may not be your total pump's capacity today. And if you ever want to optimize a plant and you don't have the correct pump capacity or the correct blower capacity, or a correct hydraulic bottleneck, it'll be a false optimization. So one of the things which was a driver into building this is to avoid those things which you get trapped in a design model. And so this required re-architecting the whole thing and starting all over from an asset base, which was a lot more effort, and being able to connect to real life conditions and enter real life conditions. So you have the grid tanks here. So I've set up the 2 grid tanks. I'll connect it up. I will also go into this grid tank and I will turn tank number 2 off. Let's say this side of the plant is not operating. Now if I go in here, it'll say, okay, I have 2 tanks. Only one is available. The other one is not available right now. I've turned it off. So then we go back here and let's say after this grid, I will skip equalization because of time in this class, and I'll put in a primary clarifier asset group or the primary clarifier system at this stage. So really this here should be called grid system, and then under that you'll have tanks, etc. And this is primary clarifier system over here. Okay, or primary clarification system. And within that you will have tanks, etc. as assets. And you can have pumps as assets. So within the primary clarifier system, once we get into primary clarifiers, it gets into where biological models do play a role. But you do have the ability, if you want, you can turn the model, the biological model on or off. Now, down here, this is a detail, but you can have a local model which is associated with the primary clarifier, which is different from a global model which is being put into every part, everywhere you're running a biological and a chemical model. Now, what I often do for primary clarifiers is I shut off the methanogens. I keep the fermenters running, I shut off the methanogens because the sludge layer over there is not enough to start generating methanogens like an anaerobic digester. It just confuses the run sometimes. And so I like to shut it off and I use a local model. But today, when we are starting, we'll just shut this. We will not run a biological model in the clarifier. Okay. So what I'll do is I'll set up the primary clarifier over here. I'll start with the tank. Now for the tank, let's say this is the primary clarifier tank. So I'll call primary clarifier. And let's say the depth of your primary is 10 feet. For those who have a license, I'll just send you the file and you can just switch it to metric units. Don't worry about the fact that we are using US units today. It's very easy to switch it around. Just by switching units here, you'll get it in metric. Okay, now let's say this plant, I started with a small plant, 2.5 MGD. I didn't want to make it complex plant with 6 clarifiers or more or something like that. I started with a simple plant. Now, within this, let's say you have 2 clarifiers and today you're operating 1. So right now it's just showing you 1 circular cell. So this, I'll rename this primary clarifier 1. Okay, let's say this is circular with a diameter of 70 feet. But now I have 2. So I have to go back here and say, okay, where is my second one? Let me add that second one. You go in here and you click on these 3 dotted lines beside the cells and you press on this and you say, okay, this is a circular clarifier. And so it has given you another circular cell here, and I go in here and I call it primary clarifier 2. And do not worry about how you spell it today, what you have spelled it. You can always go back and edit the name and it's fine, you know. But don't make the mistake I just made. I made it some 70 million feet diameter. Now let's say primary clarifier 1 is not operating today and I want to shut that off. Okay, fine. I shut off primary clarifier 1, 2 is operating. Now, you can shut it off here or you can shut it off through a SCADA link. It depends on how sophisticated you want to get. But again, the point here is one of the first points we were working with, they said they do not want to load a new GUI every time they change the trains in operation and have to rerun the whole thing. They want to be easily able to shut things on and off. And they even want to be able to run parallel scenarios, one with it on, one with it off. So you can add scenarios and run it with everything on, etc. for the same flow. So that was one other objective. So now we've got the tank set up. Now there is another thing called the underflow controller. This is controlling the flow out of your primary clarifier. So let's call it primary sludge underflow. So this is the primary sludge underflow controller. It is asking you what is the flow rate. Let's say we want to enter it in gallons per minute. Okay, and for a small plant like this, let's say this is 10 GPM. For clarifier, only 1 is operating. Now, what happens is when you change the underflow on any particular day, this underflow again can come from SCADA. And in SCADA, in the Excel file, how we set it up is there's one which is running with the last 24-hour average and another is real time. So it will bring both in. You don't have to get locked into, okay, at 2 p.m. my underflow was 12 GPM, and on a daily average it was 20 GPM. It will bring both pieces of data in, so do not worry about that. That's why you have the dynamic simulation time series data which captures the variation. So now you've got that part here. So now, when you have a clarifier, we are not going to set up a sludge handling system today because of lack of time. But it is easy to set up. What I'm going to do is I'm going to link this to as if the sludge is getting hauled out of the plant. Just go, and if you have a license, when you download the files, you will see that there are files where the whole sludge system and a complex one is set up. But today, for lack of time, I'll just end this on a sludge, and I'll call this primary sludge underflow. So I'm spending a little bit of extra time here so that I start building it in a little bit of a disciplined manner. I could decide not to rename the things if the hierarchy kind of tells me what is where. But I will spend a little bit of time renaming this, and I'll call this flow stream. You have all these flow streams. I'll call this raw influence flow stream. All right, flow stream. Because when you get to viewing your results, it helps to have the streams named rather than just the default name. So I'll call it screening, RI screening, effluent flow stream. I'll just put FS for flow stream. I'll call this grid effluent flow stream. Now, after this primary, I am going to put in, I'll tell you why I'm doing this, but it will be very obvious to you. I'm going to put in a flow combiner here because the RAS will come in here and join up. So I've connected these two. Now, this is your primary effluent flow stream, so I'll rename this here. Primary effluent flow stream. Now, this is a combiner. I'll also rename this combiner. I'll call it PE-RAS combiner. PE and RAS. Now, what I'll do is today I'll set up an MLE type of a plant. And for this, I'll go in here. There are many different types of bioreactors. We will just cover one bioreactor today. Just the basic SGM bioreactor, not the biofilm or the membrane or the SBR or other types of bioreactors. We have plug flow bioreactors, etc. So now within the bioreactor, let me call this anoxic one. I'll call this anoxic one system or anoxic one zone. Okay, maybe the system is not the right word, but anoxic zone. Okay. Within that, it is asking you, okay, how many tanks do you have? That means if you have parallel trains, and let's say this plant has two parallel trains, it's just a simple two parallel trains. You want to put in the tanks for each. So it asks you for a depth. Let's say this tank is 12 feet. Now, let's say you have two parallel trains, and you want to put both in rather than put one number. If you have three, you would put three in, and then you can turn the ones you don't want to run off, or if you want to run on, you can turn all of them off. So now I have two rectangular cells, and I'll call this anoxic train 1, zone 1. Okay. And I'll call this anoxic train 2 zone. Okay. So now it is asking for the dimensions for each, and I did do a little bit of homework unlike the last class to get to the right dimensions. Let's say this is 60 feet and this is 30 feet. And this one is also 60 and 30. Okay. Now, let's say today I decided not, or this month, or this half of the year, because my flow is too little for this plant to run both trains, at least in the fall and summer, I am going to not run train 2, so I will show this out over here. Now, within a within a tank, right now it's showing as aerobic tank. Yeah, if it's a swing zone and you want to switch it between aerobic and anaerobic, you can set it up that way. If it is a dedicated anaerobic and you do not have diffusers, let's say I do not have diffusers, I just go here and say none, and I'll set this up as none. Okay, so it becomes anaerobic over here. I will see if I can. The variable volume does not apply this in an anaerobic tank. In this case, the depth of the tank is not going up and down. The dampening flow is a concept which, let me see if I can cover it today, but it is more for advanced use, why you use dampening. So, now, this point is going to have a nitrate recycle, and so the nitrate recycle comes into this zone. So I'll go in here and I will select another combiner from here, and I'll put this guy over here, move this around a little bit, and I'll flip this around, and I'll bring in the nitrate recycle over here. And I'll call it, let's say over here, PE RAS nitrate recycle combined. So let me join these up. This up. If you want, you can name this flow stream PE RAS. And this one is PE RAS nitrate recycle. Yeah, this may be a virtual thing built within this, and there are ways to understand that. I'll get into that as we move on. Now I want to add another bioreactor here for the second anaerobic zone, which I will put in as a swing zone. Okay, so I get to the second bioreactor. I will call this. Let's say we want to call it swing zone. And let's say the plant uses a number and it calls it 2. Okay. I'll keep the model active. Let's say this is also 12 feet in depth. So that's fine. Now, here is where, okay, let me first finish up the tank and then I'll call this, okay, I'll call this anaerobic, the first one, anaerobic. Zone 1 tank. Just to make sure that this, I'll call it swing zone tank. Okay. Now, again, it's asking me for the dimensions and whether there's 1 or 2 cells. Let me just quickly enter the dimensions here. Now, it's a, okay, that's it. Obviously, this plant, if I have 2 of the first cell, there will be 2 of the second cell. So, this is swing zone 1, train 1, and this is swing zone 1, train 2. So let me make sure I get one of the things, before you run it, the first time you're setting it up, you need to check that you've set up your dimensions correctly. You didn't leave it as the default. And number 2, I'll turn number 2 on. Now, there is a second way to turn it off, that is as if it is connected to SCADA here, the SCADA link, whether if it is 1, it will be on, if it is 0, it is off. Okay. So I've set up, now comes the tricky part, how do you set up a swing zone versus an anaerobic zone? So here in the diffuser, here in the swing zone, you can keep the diffuser, say diffuse aeration, and you can just turn this guy off over here, as if it's SCADA or a valve you have is turning it on and off. And automatically it becomes off. When you turn it on, you turn it on here. You also have another location where SCADA link up turns it on and off. When you set up the diffusers, you will go in here and you will enter the alpha, hydro diffusers, etc. I will change. Let's say these are pretty good diffusers, 24% clean water efficiency. I will not set up the blower group today. I will not set up a monitor. It just is not enough time. In a more advanced class, we will associate blowers because you can have multiple blowers in your plant. Some operating aerobic digesters, some operating this, and you can set up which blowers can work where, and you can also have blowers switch around and supply different parts of different depending on what is available when. So we have set up the swing zone. Let's quickly go in and set up the rest of the aerobic zones. Go through and set up the aerobic zones here and the nitro reset. And I'm just moving these things around. You just press one mouse down, and with the other just drag and move it where you need. You can also move it in small amounts by using this move right or move left thing and fit everything into your Geo screen that you have here. So bear with me, I'll quickly go through the aerobic zones right now. Let's say it is also a 12 feet depth, and I'll call this aerobic zone 1. And within that, you have tanks. And within this, you have 2 cells. So I will go in here and add the second cell for the 2 trains. And this is the last one here. Rename the section. Zone. Train 1. If this is taking too much time, I can switch over to the file that is already set up. Now, when you get to diffusers, it becomes important. There are some features here. Let's say this diffuser is 24%, 12 feet depth. So you got all, and you have your alpha, and I'll leave that alone right now. Now, the set point controller. This is your DO set point. You can bring that in from your SCADA system through a link, or you can enter your actual operating value. Let's say you're operating at 2.5 right now in this aerobic zone. So you enter it here. If there's a time series and you want to bring it in as a time series, there is a way you can bring in time series data over here in a time simulation. Okay, so the diffusers are set up. Now I will collapse this. And I'll bring in another, there are 3 aerobic zones, let's say in this one, all 3 in. I will change the dimensions of the aerobic zone later. I will get to a clarifier right now, or I will just show you the other part. I will now add in the secondary clarifier. Let's say this is my secondary clarifier. I put it here. And I will link these guys up. Okay, I need my nitro recycle pumping system, which I need to put in. So for that, it's the way the nitro recycle is built for making it efficient is we put it within. Right now, the system is put in within a flow divider. That means that you're going to split part of the flow coming out of the tank back to the nitrate recycle system. So I will call this nitrate recycle system. Now, the nitrate recycle system may have pumps within each train. Let's say you have 2 pumps per train. So you have 2 trains, so 4 pumps. And you can dedicate pumps to trains, all that is fine. I will flip this like this. I will show you how the nitrate recycle is set up, and let's say the nitrate recycle is right now operating at 5 MGD for the 2.5 MGD plant. I will link this guy back here so that the recycle is going here. And I'll connect these two. I will just for a moment name the flow stream or nitrate recycle flow stream. Here, I will call this anoxic 3F, anoxic 3, no, aerobic 3 effluent. 1, 3 effluent. I'll call this secondary effluent flow stream. I have not had the time to correct the dimensions of this. I want to focus on the clarifier. So the secondary clarifier here is similar to the primary clarifier, but we'll keep the model running here. Let's say the depth is, let's say your clarifier is 30 feet. I'll put in the depth here. You have to put in an underflow. What is your underflow rate? That means your underflow, which is sometimes you call it RAS, and then there's a Y. So we'll call it secondary clarifier underflow, and let's say this is operating right now at 1.50%, 1.25 MGD. We'll call it secondary clarifier underflow controller. Okay, now the clarifier, assume this plant also has 2 circular clarifiers. So I will put in these 2 circular clarifiers, and let's say each is 100 foot in diameter. So this is secondary clarifier 1, and this other guy is secondary clarifier 2. But right now, because my plant is underloaded, I switch number 2 off. Okay, so if you go in here into the secondary clarifier tanks, and you look in, if you look here, it says there are 2, and 1 is available, the other one is switched off, either for maintenance or you've just switched it off. Okay. Now, there's another thing I had mentioned. There's the lab section for the secondary clarifier. If I open it up, it asks you for SVR, unstirred SVR. And let's say this plant right now is operating well and its current SVR is 100, so I can put that. So it is treated as an asset, SVR is treated as an asset. So now coming out of the secondary clarifier is the RAS line with a WAS flow splitter. So what I will do is I will go in here and I will put a flow splitter for the WAS. I will do a flip. I will connect this to this, and I will close this loop over here for the RAS. Okay. Now, just to keep things simple, today no sludge handling, but we still need to close the loops. So there is an effluent. We are not going to put in the chlorine contact tank or the filter today, and the filter recycle from backward. All that is for a more advanced job. We are going to put in the sludge here. We're not going to put in a sludge holding tank, the digester, a thickener, centrifuges, etc. All that, again, we can handle in a more advanced class. We do need to put in a wasting rate. So let's call this WAS system here, and the WAS flow controller. And let's say the wasting rate, if I want to enter it in GPM, right now is over here 20 GPM. at this point. Small jump 20 dps. We'll see if this works out when we run. Okay, so where's the setup? This one is the secondary clarify underflow flow stream. Here, this is the RAS flow stream. I'm just naming it because when we run it, this is the WAS flow stream over here. So this thing is closed here. What I have not set up as yet, just to show you for the sake of time, is this second zone. So let me just take a moment and set up aerobic zone 2. We're almost done with the plant setup now. Aerobic zone 2. Okay. The tank, aerobic zone 2 tank. So there are two rectangular cells here, so I will go and add the rectangular cells, and now we have two rectangular cells. This first rectangular cell, again, I'll just put the dimensions over here. And I have to remember that this thing is shut off, the train tube. Okay, and then the diffuse aeration, it is asking for what is my DO set point. Let's say here I'm tapering down the DO as I'm moving down, and this is 1.5 feet. Diffusers, I'll just correct this to be 24%, 12 feet. And let's say the alpha is 0.65 for here in this. Now the third and the last aerobic zone 3. Now, how do I decide? Well, one good question is, how do I decide how many aerobic zones I need? So there are some, and what we like to do is we like to be real, because here this is an operations model which can be used for design, for asset management. So I like to look at, yes, physically how many baffles there may be in the aerobic zone, but also how many droplets of diffusers are there, and how the mixing, longitudinal mixing is around the aerobic zone. In some cases, there is such general mixing that it acts more like a plug flow, and if there are 6 droplets, it may be that it operates, the first one, there is more swirling over here, and you have the first aerobic zone as one, and then you decide, okay, there was just one baffle, but you split up the second aerobic zone into, let's say there were 3 droplets. Or 4 droplets. You split it up based on the number of droplets into distinct zones. Why do we do this? Well, the reason that you try to be more accurate in simulating your aerobic zone is because if your plant is really more like a plug flow and you just model it with one aerobic zone, you will have a real tough time getting an accurate result, irrespective of which model you're using. The kinetics are not going to get simulated correctly. So it is important to get the actual hydraulic mixing in the aerobic zone and the number of droplets, and then plug that in. Because if you're going to use this as an optimization tool, your tolerances for your effluent here are much finer than as a design model. As a design model, I can just design it and say, oh, I got 0.5 milligram ammonia, I really need to get stable at 1, this is fine. Or I'm a little off, let me add some more bioreactors, and this is fine. But here, you're actually trying to simulate reality of what is happening in the plant. So we do use that in a discipline now. Real plants, if the 2 trains have 2 different aerobic zone fractions, or if there are 3 trains with one type of aerobic zone fraction and the others with a different type of aerobic zone fraction, so 4 others, you will simulate those as different offsets over here, and those train groups will be different. So that often happens at plants. It happened at Westminster, it happened at USA, it happened at Thousand Oaks, and I think it will keep happening over and over again as you get to more complex plants. Westminster, you have two different types of diffusers, two different parts of the plant. So you cannot just group them and do it that way. Thousand Oaks has different aerobic zone volume fractions built at different times. USA, same thing, built at different times. So then we simulate those separately. So for those, you do make the effort to be real. But once you do it, then you have very detailed knowledge of the plant, which you otherwise do not have in a model. Tomorrow I will show you how you can put in assets and link photos and drawings, etc., and valves, pictures of those into the system and have it as a knowledge repository. So I think now I've got everything. I'll do one quick check that I've got the check I'm doing is I'm looking at these volumes and making sure these volumes look correct. 43,200 cubic feet. Okay, obviously this one is off and this one is off. I forgot to enter the dimensions correctly somewhere. So let me see what I entered. 60, 30, 60, 30. So what is this? What is my depth? Oh, I forgot to enter the depth here. So the depth was the default depth. So that, and here I have not set this one up with the proper dimensions. So this zone 3 group. The depth is 12, and then I have only one rectangular cell with wrong dimensions. The default, so I put this as 60. And I'll put this as 30. And then I will add another cell here. And so this also I have to get the dimensions right. Second one is off. Okay, now let me look at the 43,200 is the volume here. That is fine. Don't worry about the effective volume, that will get corrected when we run it. Again, the tank group here 43,200. So that is correct. The secondary clarifier, I'll do a quick check of the clarifier. Okay, the sludge removal efficiency right now. Okay, this is the solids removal across the clarifier. I just entered 99.8. But we will talk about it more when we get into a deeper discussion of clarifiers in another class. Okay, I think I have got everything set up except for the flow stream names. I could call this aerobic zone 1 effluent flow stream. This one is swing zone effluent. This one is an oxide one. Okay. Now, saving a file. Saving a file is very easy. I'll do a save as, and rather than select one of these other names, I'll call it basic plant. I'll call this class 2, and I'll save this. So it has saved it. If I now go into this folder, I will see that it has saved a basic plant C2 IVO and an IVO1. So this is where all these dimensions of the tanks and how it is configured is here. IVO1 doesn't have much because we haven't run this as it, but the file is saved. Now, when we get to running it, there are some options that you need to be aware of. First, it's always best to run calculate flows only, just to check your hydraulic network. I will not change all these at this stage. Then we will run it with an initial guess, and in a more detailed plan, we are supposed to refine our initial guess and get to more real values of initial guess. Okay. Then there's dynamic simulation. Let's see how far we can get through with that. So now let me run just the calculator flows only and see what happens. So it says checking network, hydraulic network is okay, all that is done. Now if you click on these flow lines right now, it's giving you the flows at each point here. And you can change the units in which you want to save. If you want to see this in GPM, that's fine, this flow stream. So it's giving you the nitrate recycle. Click on this, it says 5 mgd, so all that is done. And the effluent flow is 2.46 because there's some sludge wasting, and this one is 0.03, but if you want to see it in gallons per day, that's 28,000 gallons per day of waste. So let me just save this one out, just save over it. Now I want to change it and run the actual model. So I'm not going to do calculate flows, only I do steady state. It is good practice to get to reasonable values of initial guess and reduce the microbes which you don't expect to exist in the system. But let's not worry about it. I just run. So I press run, and it starts running, and it is working through the convergence. And there are ways to speed up the run for a complex plant, and we will work with that in a more advanced class. So let this run get over. So once it reached the target error, it has finished the run. It hasn't shown any errors. Now what I'll do is, I don't want to run from an initial guess every time I want to run it. Subsequent runs will be from the end of this run and whatever mixed liquor it generated. Okay, it showed I had 3620 mixed liquor and ammonia of 1.35. Okay, what I did not do is set the temperature. Let's say the temperature is 18 degrees Celsius, and the air temperature, let's say, is 15 Celsius. The ammonia is a little high. That's fine for now. What I want to do right now is get to a little bit more advanced tech. Okay, let me save over this file. I want to set up an MCRT calculator. I want to check my MCRT. And in this, you can have as many MCRTs as you want. You can have sludge ages. Things want to want the sludge ages. What else? Sludge age was based on primary effluent or raw effluent. Suspended time. Fine, we set it up. They wanted SRT, which is different in their definition from MCRT. So we can do all that, no problem. So you go to the calculator, you select where you want to, which parent asset you want to put your MCRT in. So we'll put it under the plant, and we say MCRT. Okay. So add a child node called MCRT calculator. So now I'm setting up an MCRT calculator here. But I can rename this MCRT secondary treatment, no class. I'll set up another one with secondary class. So when you get into this MCRT, it's fairly simple. It's asking you which modules, acid groups, are part of your MCRT. So you select anoxic, swing, aerobic, 1, 2, 3. You don't want to include clarifier because you said 1, 2, 3. Flow streams. Now it'll ask you, and this is where the naming of the flow streams comes, what is carrying the sludge out of the system? So the gas is carrying it out, and secondary effluent is carrying it out. So I run it again. Finish that. And I look at the output. There's something wrong here. What is it? Why is the MCRT 0.2 days? Did I set it up correctly? F2 and flow stream. I have to check where is flow stream, secondary F2 and flow stream. This is not secondary F1 was not named, so I put the wrong flow stream. I don't know what flow stream this is secondary influence. I named it incorrect. This is secondary influence, this is secondary influence. So now I have to go into the MCRT calculator and make sure I got the right flow stream. Select the secondary effluent flow stream. Now if I check the output, 8.9 days. It's a little too low, the secondary, the MCRT, and that's why my ammonia is a little high. I could reduce the wasting rate here to maybe go in here and say, okay, it's 15 GPM instead of 20, rerun it. There's another reason it's giving this. I did not go in and change my default primary clarifier sludge removal based on primary clarifier suspended solids removal. So once it's the depth cut state. The depth is incorrect in one of these tanks. Well, this is okay. Let me do one thing. I have not used the dampening flow as yet, but I'm going to use a trick here. I'm going to increase my nitrogen to I'll tell you why a little bit later. To make it converge a little quicker. And I'm in the primary clarifier here, probably it has 60%. It's an underloaded primary right now, 60% solids removal. So I'll rerun this with this new solids removal. So it ran. Yeah. So if you look here, and you can look in the results too, the primary effluent has about 100 TSS. If I look here, 170 DOD. But if you look at the COD, about 320 COD. If you look at the secondary effluent, this one has an ammonia of 1.23, a little high, higher than what I want. And a nitrate of 5. If I look at the mixed liquor going into the clarifier, it has 3,600 mixed liquor. So I have a few options. I could go in here, and if you run an optimizer, it will automatically tell you that. You could go in here and you could select your DO set point and you could adjust that. Also, I believe the kinetics that are set up are a little on the conservative side for for some of your, at least for nitrification, for some of your plants. So, so we do a calibration, typically winter and a summer calibration. So I've now increased the DOs. I'll rerun it. And right now the ammonia is 0.82. Okay, I'll stick with that. I will save this file. So if you want to run another MCRT, let's say you wanted to run an MCRT with, I know that those who have to leave, that's fine. But the only parts left are just showing you a little bit of dynamic simulation. So I want to run another MCRT calculator, and that's it. This is with clarifier. Okay, so I set it up with clarifier. I select the modules here. I go in here. With clarifier means secondary You can have an anaerobic digester MCRT, you can have aerobic digester MCRT. Same thing with hydraulic retention pumps, we do the same, we set up a calculator. Just select the right flow streams, yes, secondary effort, and so on. Another calculator, and then run that, and it's about 13.75 days with the clarifier, but I didn't change my default sludge run to about 11 and a half days without the clarifier. So now I got that part going. So now, the last part I want to cover, even though it's not a part of this class, is dynamic simulation. So I will, let's say I want to run a time dynamic influent pattern. What you go in is into the raw influent, make sure you're on the input tab of the raw influent. And you have to do two things. One is you have to say where that data is going to come from. So you have to attach an Excel file. And I will attach this particular Excel file that I have and assume this data is being updated from SCADA, written into Excel. There are pieces of software, commercial software available. And you may already have software that can write this file once every day with 15 minutes. What we use is 15-minute average data. If you want, or you can extract it periodically, or you can extract it and in every 15 minutes and have it feed in with the 15-minute data. There are different ways to do it. But I will connect to this file and to this column in this file. So this is a little bit more of an advanced feature, but I will do this. So first, it says attach. Okay, I go to this attach and it asks me, okay, what file? Where is this file? So I go look for this file, and this file is sitting here. And we only allow Excel SX, even if you're using Excel 2003, save it as an Excel SX. So now it knows it is on my computer, or whichever computer you're setting it up, or if it's in the point computer, it knows where to go in some directory somewhere. It doesn't have to be local. It goes there, it knows the file is available. Okay. And the file can keep getting updated. It reads the saved version of this file. So you can keep updating and writing to that file every day, and it'll pick the saved version for that current date. So now it has done. Now it says, okay, is this default value linked? If you want to link the default value, you say yes. Okay. Then it says, okay, which file are you linked to? Okay, influent pattern 1. Okay, that was the file I selected. Which sheet? Well, it's in sheet 1, but if the sheet is named, that's fine. Which cell? So I need to look here, and I'm going to connect. This is where my influent data is, J1. Okay, so I will go in here and say, okay, cell J1. Okay, now if I run it, or if I say import, okay, so the start date. Now it is using today's start date, but I can say, okay, this is not really the start date of this data. This was 11, I think this was 11/17 start data. Okay. 11/17 at 0000. So now it has imported that value. The next thing is, how do I import the time series? So this is the average value. So to select the time series data, you have to first, it's saying none. And if you try to do this, it'll only give you none till you set up the time series as another asset. So I go in here and I click on this, and it asks you, is it a recorder or a scheduler? For this class, just use a recorder. Scheduler is if you have a schedule of flows that you already know. And it's an advanced concept. We will cover that later. So this is your flow recorder data, recorded into some machine somewhere, into some chip or some database from which that was extracted. So I can rename this and call this, okay, RI flow recorder. So okay, this is RI flow recorder. Now it asks you, the recorder has to have a pattern, because you can have multiple patterns and how it gets into an optimizer issue there. But okay, this is pattern 1, and if you want to name it RI pattern. Okay. So now I've got the pattern. Now you click on this for the pattern. It'll ask you, where is this pattern linked to? You click is linked, you select the file. You can have multiple Excel files. You can have lab link. Now it's saying, where does this data start? Which cell? So I need to look here. It starts in J11. Okay, so I'll enter here. So J11. If I click import, now I actually have 7 days of data, but I haven't as yet set it up to bring in 7 days. It just brought in this 1 day of data in. So you can see this 1 day of data. If you look in the Excel file, the graph over here, where did that graph go? I had a graph. It's lost. Anyway, I put in a graph in this Excel file just before the class. There it is. So this same pattern is being brought in. Now I can run 7 days if I want to, and I might be able to do that. But let me first start with 1 day. So it has brought this pattern in. I could link to a waste, same thing, I could set up a waste sludge flow stream, which brings in daily waste rates, which may be different from 1 day to another over a 7 day period. Now, when would I run a 7 day period versus a 1 day period? Well, I can have a scenario which runs a 1 day period like here, and I can add another scenario to this thing and say, okay, I want to run 7 day at any time in this scenario. I'll just call it 7. I can run a 7 day scenario here and a 1 day scenario here. I would run the 7 day if I'm anticipating a wet weather over the next 7 days and put in an assumed flow pattern for that. You can do all that and see how it behaves. So okay, so now I'm going to finish what I was doing here rather than get distracted with all the other tools. I have now set up a time series data, and I said this is in the long-term flow record. Okay, so I have brought that in here. Sometimes I end up making a mistake here. Okay, so now there is a round flow recorder. I'll just run it steady state once more with this 2.65 MGD real flow. Okay, so that ran here by mixed liquor right now is like 3724. My ammonia is 0.89. Now I switch it to dynamic simulation. You can run dynamic simulation on this scenario, or you can create a separate scenario and run it over there. So I've switched it to dynamic. In dynamic, I am going to, if you look at dynamic, I'm just going to run the 96 time steps right now. Okay, 1 day. So it's running the dynamic simulation. It's going through the time steps. Okay, so it finished the dynamic simulation. Okay, and save it to a different file. Some people have to leave, I understand. Okay, it's saved to a different file. Okay. So now if you want to look at the results for the dynamic simulation, there are different places to look at the results, but the best place is to go to results. And go to the flow streams. Where are the flow streams? Here. Go to the flow stream, look at the round flow and flow stream. Oh, I have to say, because we did not want to overload the data file, I have to say which flow streams I want saved into dynamic simulation. So let's say I want raw inflow flow stream, I want anoxic 1 effluent, I want swing zone effluent, I want aerobic zone effluent and secondary effluent flow stream saved into the dynamic simulation. So I run it once more. Unfortunately, I forgot to say that. But once you set it up once, you don't have to keep messing around. I started from scratch here, so that you can get a feel of it. Now, if you go into the results, you go into flow streams. Let's say the raw flow and flow stream. So it's showing you the raw flow and flow stream. The flows were here. If you go into the secondary effluent, and I can highlight which ones I want. Secondary effluent flows, secondary effluent ammonia at different times of the day. This started at midnight, then in the early morning hours, the flow was very low, and then it picked up, etc. So it's doing this diurnal pattern. So it does that. It shows you your nitrate pattern over the nitrate pattern over the day. So that shows you the dynamic simulation also. So this is probably a good place to end here. I do not know if we have enough time to do dashboards today, but you can set up a dashboard it's like a SCADA dashboard, and you can say, okay, I want to see my raw flow being updated all the time. I want to see my aerobic zone effluent. You can select which panels you want on your dashboard, and you can dock them. And if you have a large monitor, you can dock as many. This is mainly for the plant. I'm not running an optimizer, so we won't give you the optimal solutions. And my secondary effluent here, what the characteristics are, how much ammonia, etc. And this is the last time step of the dynamic simulation. So that is the dashboard. It last me. Do I want to save the dashboard? So that essentially covers everything for this class.